Okay, in this lesson we're looking at what I call the special quotient rule, or simply just looking at the integral of 1 over x resulting in a logarithm. This is our general formula, and you've seen that before. You know that the integral of 1 over x is ln x plus c. I'm going to take that a little bit further, and we're going to look at it as in two ways. So we'll start with a derivative. So it will be the derivative form is that d dx, or the derivative of with respect to x, of ln of any function will be equivalent to the derivative over the original function. Now you can see this here. So when you look at the derivative of ln x, it's pretty straightforward. So if the function is x, so f of x is x, the derivative of that will simply be 1. Then if we follow this f dash of x over f of x, it will be 1 on x. And this holds true for all of these scenarios. It's much quicker than going through any other process trying to apply it to a chain rule. The special quotient rule speeds this up a lot. So another example, and it can be any type of function, would be we're looking at the derivative of ln sine x. Okay, so we've got an internal function of sine x, which means that f of x is equal to sine x, and the derivative of sine x is cos x. So that means that this derivative will be the derivative of the internal function over the internal function, which will be cos x on sine x, and we could just say that is cot x. It's a one-line differentiation. Okay. Another quick example would be looking at the derivative of ln 2x squared plus 3x take 7. So again, we can say that f of x is the internal function 2x squared plus 3x take 7. The derivative of that is 4x plus 3. And so therefore our derivative of ln 2x squared plus 3x take 7 is simply 4x plus 3 over 2x squared plus 3x take 7. Okay, so simple. Now that's not the goal of this lesson. The goal is to look at the integration technique utilizing this, but hopefully you can see that using this in differentiation makes our process much easier as well. Okay, so when we look at the integral form, it really is the same thing. We're saying that the integral of the derivative of a function over the original function will be equivalent to the natural logarithm of the absolute value of that function plus c. So really, if you can see a relationship, and we'll look at a simple example, we'll look at the integral of 2 over 5x plus 3 dot dx. The whole process here is to make sure that this can be f dash of x, and this will be f of x. Okay, so if we let f of x equal 5x plus 3, then we need f dash of x to be 5. Okay, so to turn this into 5, we need to multiply by 5 and divide by 2, right? So that means that what we're looking at is that the integral of 2 over 5x plus 3 dot dx needs to be 5 over 5x plus 3. Now, in order to make this 5, we've multiplied by 5 and divided by 2, right? So that means we need to do the opposite. That means we've got 2 on 5 on the outside. So if we can perform those little manipulations, then it simply ends up being 2/5 ln. Our internal function is 5x plus 3 plus c. Alright, so we'll look at another example. Okay, so if we look at this scenario, we've got the integral of x squared plus 3 over x cubed plus 9x plus 2. So again, we want to take a similar approach. We want to say that f of x is equal to x cubed plus 9x plus 2. And if we can see a derivative relationship between the denominator and the numerator, so f dash of x is 3x squared plus 9, I'm hoping that you can see that that is 3 lots of x squared plus 3. All right, so in order to make this numerator the derivative of the denominator, we need to multiply by 3. So if we do that and we multiply by 3, we get 3x squared plus 9. But in order to not change the value, if we're multiplying by 3, we must also divide by 3. So we're multiplying the entire integral by a third. Once we've got that, it's simply 1/3 ln x cubed plus 9x plus 2 plus c. All right, so I told you this was going to be a quick lesson. That's it. It's just utilizing that special quotient rule with derivatives and integrals. This will become very important when we start looking at a process called integration by partial fractions. Okay, thank you for listening.